Thank you very much for this lovely introduction, and thank you very much for the invitation. I have really had a fantastic day so far. I am giving this talk on behalf of the eROSITA consortium, German consortium specifically. I'll tell you a little bit about that saga. But majority of this work actually is a production of large number of people across continents. The science results I will present are from my group at the Max Planck Institute for Extraterrestrial Physics. Before we delve into the details of the eROSITA's distinct view of our universe, I will tell you a little bit about our universe and put everything in a larger context. So if we go back all the way down, the beginning of time, right? So everything started with Big Bang right here, and the universe after Big Bang rapidly expanded. What we call this era is an inflation era. The universe at that time is very hot and dense and does not emit any light to us. And briefly after that, when the universe was actually expanded enough and cooled down, the protons and neutrons started recombining. That's called the recombination era. And all of a sudden, it became transparent to radiation. And when it became transparent to radiation, a relic radiation CMB, cosmic microwave background, was released. So cosmic microwave background basically is a relic radiation from the infant universe. When we are talking about early time probes during this talk, for example, like Planck CMB results, we are talking about an infant universe here. Then universe keeps expanding, and we basically, it follows, the dark ages follows, we don't get any light, and it cools down enough that we start observing the structure formation. In the hierarchical structure formation of the universe, we see the stars forming first, then the galaxies form, and the last leg of structure formation, we observe the formation of the clusters of galaxies. These are the largest dark matter halos that we will be talking a lot about today. And basically, the late time probes like SRG and eROSITA is on board SRG, basically is a late time probe. It probes the universe in the last 5 to 7 billion years ago. So late time probes basically look at this era in the universe. So we can learn a lot about looking at the data from late time probes and comparing them with the early time probes like Planck and understand the fate of our universe. So this is what we would like to do in the area of precision cosmology. So when we talk about precision cosmology, really the state-of-the-art cosmology results are still from Planck. What Planck did is looked at the cosmic microwave background and calculate the angular power spectrum of the cosmic microwave background to get the signal. When they fit their model, they could measure fundamental properties of our universe with an unprecedented statistical precision. So some of these parameters we will talk a lot about today is the energy density of dark energy density of total matter, omega m, and sigma 8, that's the normalization of the density fluctuations in the early universe at 8 megaparsec scales. We will talk a lot about these three, and then it could measure the Hubble constant. It can also measure the some neutrino masses and the equation of state of dark energy. Assuming that it's a dark fluid, actually it has a equation of state that is pressure divided by its density. So look at these precision. I mean, it is stunning, right? And you might be wondering, if Planck gave us all we want to know about the universe, why are we doing cosmology, right? So that is a very good question to ask, and here is the answer. In the last decade or so, there were several tensions arising in the cosmology, and they are very intriguing, right? When you have a tension, there's something that you can work on. Maybe there's some new physics, but there's definitely funding, right? So One of the tensions is, of course, is a well-known Hubble tension. We're not going to be talking about Hubble tension today. We're going to talk about the other famous tension, which is called S8 tension. But what is S8? S8 is a parameter which combines the density fluctuation, normalization of the density fluctuations with the energy density of matter. Why do we combine? Because these two parameters are correlated with each other. There is a huge degeneracy. When you combine these two in a parameterization, which makes sense, then it's easier to compare different cosmological probes, which are different to different parameters. So this is the most ideal way of comparing late-time probes with the early-time probes. So here is the Planck measurements of that S8 parameter, is a parameter in yellow, and all the late-time probes basically find an S8 parameter which is 2 to 3 sigma in tension with the Planck observations. What do they really tell us? What does this S8 parameter? So S8 parameter gives you the clumpiness of the universe, basically the seeds of the matter that we expect to see in the early, for example, universe. But late-time probes don't see that much clumping in the universe. Late-time probes say that, oh, okay, Planck has overestimated the structures that we see today. So what is really going on? There are multiple models which could explain this behavior. Maybe there was a new physics, a different component of dark matter which affected everything, or different component of dark energy even pushed the universe down and slowed the structure formation. You could explain that with a lot of exciting physics, and theoreticians are really working hard on this. But you can also turn the coin and look at how well we understand our observations. Maybe there's something in the physics that we don't understand, small-scale physics. Or maybe there's some statistical problems that we don't understand in our measurements. So this is why we need to do this measurement as many times as possible with different probes to understand the reason of this tension. And that was the primary science goal of eROSITA. eROSITA would fall right here. And I'll tell you how we make that measurement in a second. But it is a late-time probe. So what is it going to tell? So I will tell that story today to you. But let's go back to structure formation and see the structures forming exactly. How does it happen? And how do we actually measure this S8 parameter with structure formation? So this is a universe in a box. The dark energy component, the expansion, has been taken out to make everything a little more simpler. All these little dots are dark matter particles in blue. And in the very early universe, at very early times, you see this density field being homogeneous and isotropic, as you learned in Cosmology 101. But I must say that holds only at large scales. When you go to smaller scales, you will see density fluctuations, and those density fluctuations are where we will observe the structures form. So let's run this. And you can see the density fluctuations, and finally gravity. Because of dark matter winds, these fluctuations collapsed on themselves and virialize and form the structures that we see in our universe today. So these bright points are where these massive galaxy clusters are located. So we're going to be counting them today. And what you should notice also, we will talk about it at the very end of the talk, they are not alone, right? They are connected to each other with this diffuse matter, what we call cosmic web. And we can now detect that with eROSITA. But let's just start by counting clusters, shall we? So how do we do this? Imagine that box again. We do now take the redshift slices at different redshifts. So we start from one redshift. This is an example. We don't go as far with clusters, because at redshift 6 you would not see any cluster formation. But just for the illustrative purposes, so you understand what we are doing. So we draw a box universe, it's a volume in the universe, and we count the number of massive halos we observe in a box. We do that in another redshift. count how many clusters that we see in this box. Another redshift. This is now we see the galaxy clusters forming, right? And then we count how many of them. And there are in this box. And if we know their mass, we are in the game for cosmology, because this is what's called halo mass function. You see a simulation here, which is a sensitive probe of cosmology, A parameter. This is the scale parameter, and redshift. What you see is the mass, halo mass function, number of clusters or galaxy groups or halos, let's say, as a function of their mass. And you can see how the massive halos are forming, and these yellow circles are where they are. And so that's what we call halo mass function. Halo mass function is a sensitive probe of cosmology because of that volume that we draw in the universe, and also through structure growth, right? So how many halos with what masses we form in the universe will tell us about the cosmology, underlying cosmological model in the universe. This is the experiment we do. So what do we need? We need a large area survey where this survey will tell us how many objects we see at each redshift, right? So then we can count. And then we also need masses. But before we get into business, let me tell you what these clusters of galaxies are. They are the largest collapsed and virialized objects in our universe. Their masses are above 10 to the 14 solar masses, and a large fraction of their mass is in dark matter. You don't see it, of course, but it makes our life a lot easier because they are in a more linear regime, so we understand, at least we think we understand their physics. They also typically contain 100 to 1,000 galaxies, as anywhere you look in the universe, you see the concentration of galaxies, but these have really rich in galaxies. These bright points are their member galaxies. This is the brightest cluster galaxy. And through photometry and spectroscopy, you can measure the redshift or distance of these objects that you observe. What is really interesting, and here is the game changer, in between these galaxies are filled with hot dilute gas. This gas is so hot, the temperatures can reach up to 100 million degrees, and the densities are 10 to the -2 per centimeter cube. At these densities and temperatures, it emits X-rays through thermal Bremsstrahlung. So thermal Bremsstrahlung, just remember your radiator processes lecture is where you have an ion and an electron goes through nearby and interacts with the Coulomb potential of the ion. Then the electron gets accelerated and you get an X-ray. So, but the critical thing is that if you have a wide area X-ray telescope, you find large population of these objects, and that's what we need for cosmology. But also, because the dark matter halo is large, it basically captures and encapsulates most of the baryons. We do lose some of the baryons or gain some baryons, but most of the baryons are virialized in these galaxy clusters. Again, basically their number density through halo mass function is a sensitive probe of cosmology, and this is the primary probe, primary science goal of eROSITA. So let me introduce eROSITA. eROSITA stands for Extended Röntgen Survey with an Imaging Telescope Array. And when you see Röntgen, immediately you can realize that this is a German instrument on board a Russian telescope. So now you can imagine the political drama here, right? So SRG is the Spectrum Röntgen Gamma satellite, which was basically built by Russian collaboration. eROSITA was built by Max Planck Institute for Extraterrestrial Physics. It went on to this beautiful satellite and launched in 2019. But right 2.5 years after that, or 3 years after that, a war broke out, and then eROSITA was put into safe mode. Safe mode means in space telescope jargon that it does not take data. It's not shut down, but it does not collect data. So it's just in standby mode. eROSITA is a survey instrument located at L2 with its brothers, with Gaia and JWST. And it scans the entire sky this way. in L2 every 6 months. So every 6 months, we have a full scan of the sky. It was designed to detect 100,000 clusters, and we have a little less than half right now. And the primary science goal is to do cosmology with it, so you can see how it scans the data. eROSITA is revolutionary in many ways, but the idea of doing X-ray surveys is not new in X-ray astronomy. So there are multiple ways of detecting clusters of galaxies and doing cosmology with clusters of galaxies. And the first all-sky survey, the predecessor of eROSITA, was ROSAT, another German satellite. ROSAT found about 1,700 clusters. The primary science goal was not cosmology at that time, but anyway, people have done cosmology with smaller samples detected by ROSAT. Then in Europe, we had XMM Newton. In US, we had Chandra. These X-ray telescopes are more pointed observatories, so they basically observe a small area in the sky at a time. You can do tiles and then do the smaller area surveys, but not at the scale of eROSITA. And then eROSITA came, and now we have about 45,000 clusters in our disks, although we did not finish the survey. Another way of finding cluster is through their millimeter radio signals. So that happens when you have a large ball of energetic electrons in your clusters, and there are CMB photons everywhere in the universe. CMB photons then travel through clusters, and they interact with the high energy electrons, and their black-body spectrum gets shifted through inverse Compton scattering. When you look at the CMB map at some certain frequency, then you see shadows where there are clusters. And you can count them, and you can do cosmology with it. So there are very famous CMB telescopes, like South Pole Telescope is one of them. Now detected about 2,000 clusters. Atacama Cosmology Telescope is another one. In their last DR5, there's 4,200 clusters, and famous Planck, it cataloged about 1,653 galaxy clusters. So all these probes are very complementary to each other, and then we cross-compare what we find for cosmology. So this map, probably you have seen this map before. It is the most detailed way of our X-ray universe. Now you see two hemispheres, right? So north and south. In this map alone, there are 1 million X-ray sources. Majority of them are creating supermassive black holes, AGNs. Can you please guess how many of them are clusters of galaxies? So they look like fuzzy sources like this. Any guess? What is the fraction, percentage? Make up a number.
10%.
Good, but not close. One more, less than that. 1% are secure clusters. Yes?
Your 50,000 clusters, is that over the whole sky? Or is it
No, it's very complicated. That's half sky, but for 4.4 surveys. Yeah, so it doesn't really scale with numbers. It's really complicated because of the political reasons. But also survey that is not uniform. I will tell you a little bit about that later. So this is a good point, which brings me to actually an important note, is that in German consortium, we own the data rights of only half of the sky. So I don't get to see the north at all, or the eastern galactic half, right? So all the results that I will show you today are from the western galactic hemisphere. That was set up before I even arrived at MPE. But this paper, I note here, we discovered the south polar spur, what we call eROSITA bubble. So that's a very nice paper if you would like to go read it. Anyway, let's go back to cosmology. That's what excites me nowadays. So this is the western galactic half. You're looking at from the bottom projection. We remove the galactic center that is not great for extragalactic science. run our source detection algorithm in an area of 13.1 thousand square degree, and we find about 12,000 clusters with redshift. So this is where we actually set our detection limits very low to increase the discovery rate of eROSITA. So wherever we see 3 galaxies with a blob of gas, we said that, okay, this could be a cluster of galaxies or galaxy groups, right? So then if you just play this game, you get a lot of junk in the sample. So we estimated that purity to be 86%. You don't want to do cosmology or science with that sample. So for science purposes, we basically clean the sample. The most effective way is to increase your thresholds in X-rays. When you do that, then what you find is about more than 6,000 clusters, but we then limit the redshift range as well. I'll show you why. And when we do that, we find 95% purity samples. So X-rays will not give you complete samples, but X-rays will give you pure samples. And that's what we want. And when you have a large area survey, you find many clusters and you're in the game for cosmology. And so once you find these halos, you want to know their redshift because that's the first thing to get you to science. And fortunately, in the same year, Legacy survey team basically released their data, combined data. You see the DES tank over here of the southern sky. So we could use their DR10 for photometric confirmation, and we collected a lot of spectroscopy along the way. And so we have majority of our area covered. There are some holes, as you can see, but that's not a large area. On the right, you can see the exposure time. This is the survey exposure time as a function of survey area. So the point of this figure is to tell you doing science with this data is not straightforward because the survey exposure is variable from wherever you are in the sky. So survey depth is very shallow in the equatorial regions, but it gets really deep in the ecliptic poles. So then your detection efficiency of a source changes wherever you are in the sky. You have to be very careful. We have now a very good way of dealing with this. I will get to it in a second. On the left, you see the primary sample, the redshift distribution, and it goes up to redshift of 1.3. It's striking for an X-ray survey, which suffers from X-ray dimming, redshift dimming. In the full yellow bars, you see the cosmology sample that we do cosmology with, that 95% purity sample. The redshift range is limited to 0.1 to 0.8, where we are actually sure about our redshift measurements. We do measure the redshift beyond that point, but the error bars or the systematics in our measurements gets large, and we do not want to deal with that. We want a secure sample that we are sure of. But the primary sample does its job. It finds large number of clusters with the 68% discovery rate. Once we know the redshifts, then we can calculate the X-ray properties of these halos. The first one is the count rate, X-ray count rate, because we are a photon counting experiment. And then we can look at their luminosity or the brightness of these objects. And you can see here, this is our sensitivity limit. We don't really expect to detect anything here. If we see any data points, we say, okay, something is wrong here. Probably the redshift is wrong, right? And although eROSITA is an imaging survey, we do make the measurements of the surface brightness and luminosity very easily. We can also do spectroscopy with this data. Though spectroscopy requires a lot of photons, so we don't have the measurements of the temperature. That's what you would get from spectroscopy. But we have temperature measurements of 3,000 clusters. That is about 5% with high precision. You can see the temperature here is a function of luminosity. We are really sensitive to galaxy groups and low mass halos, and our temperature measurements gets a little dodgy at the high mass, and hot clusters and over here, and this is because our reduced sensitivity in the hard X-ray band where they would emit most of their signal. Now, let's go back to cosmology. How do we do cosmology with this data? This is the first and last equation that I want to show you today, but I would like to give you the gist of how hard this experiment is. So here is your halo mass function, the number of clusters you found in your survey as a function of mass and volume, right? So this is the halo mass function that you saw in the simulations. It's dependent on the cosmology. And here is the volume that you draw in the universe. That has also cosmology dependence. Then, that's not also over. You find clusters, that's fine. You know their brightness, X-ray properties. But X-rays won't give you unbiased mass measurements. And that's what you need to compute the halo mass function. And that halo mass function speaks to the numerical simulations. Right? So we need to find the mass. There is a way to calculate mass from X-rays, but that involves some biases. We do not want to do that. Instead, we use the least biased way of doing this. That's through weak lensing observations. So what we do is that we go and calculate the masses from the shear data. And fortunately for us, there is a tight relation between the X-ray observable and the mass, shear mass. I'll show you those scaling relations in a second. And that is basically what's called astrophysics here. Then, you do not detect the entire population of galaxy clusters in the universe because you do not have a perfect telescope, right? And on top of that, the survey depth is different, as I told you before. So if you have a massive halo, your probability of detecting it in the equatorial shallow areas is different than the deep areas in the survey. So you need to take into account where you are in the sky and what population that you see in the sky. So that is called selection function. And I'll tell you how we do this. And then we fold in the uncertainties in a Bayesian framework, marginalize over mass and X-ray observable, compare it with the numerical simulations, the emulators, and compute the cosmological parameters. So this is the game. For the weak lensing mass calibration, we work with 3 collaborations, KIDS, DES, and Hyperspring CAM collaborations helped us get the shear weak lensing measurements. So you can see the DES tank over here. All these dots are eROSITA measurements. And then we have some areas that's covered by HSC and KIDS in the equatorial regions. So this work was led by University of Innsbruck. So we tell them, hey guys, can you please look at the shear signal around this location that we find in the eROSITA all-sky survey and give us what your stacked shear signal says. So that's how we measure the mass. This is the weak lensing mass as a function of redshift for all the clusters, so no selection effects coming in here, in the common footprint between eROSITA and these 3 excellent surveys. So based on this data, we construct a scaling relation of all the clusters observed. There are more than 4,000 clusters in this plot. Scaling relations between the shear and the count rate. Translate that to mass, and then apply it to all the clusters we detect in the eROSITA southern sky. And that's how we obtained this mass redshift plot of eROSITA detections. What is really striking here, before I get to there, we actually do some comparisons with the previous measurements. We detect clusters that were detected by the previous experiments before. For example, this El Gordo is the highest redshift clusters with the highest mass. We detect it, perfect. And then we also detect what is known as the X-ray brightest cluster, RxJ 1347 with eROSITA at the correct redshift and brightness. So it's there. But what is really important here is that we will use these massive halos in a minute for cosmology. We do detect large number of group size halos, which are less than 10 to the 14 solar masses. Right, so I'll show you astrophysics results from that. And our mass limit is actually as low as 10 to the 14 solar masses, even in the first all-sky survey from the first 6 months of data. This is the mass limit which will be reached by the 4th generation CMB experiments. We are already there, and we have 2 more years of data with eROSITA to analyze. So that's really important. Let's talk about selection function. This is the most critical bit of eROSITA science, I think. So basically this work is led by MPE and IRAP in France. What we did is that basically we take the numerical simulations and body simulations where we have massive halos. We painted baryons on them using the scaling relations which are published in the literature, put them through our mock observations. We mocked the entire eROSITA sky. So we now know how eROSITA should see the universe. And then we run our software, source detection software, all our software we run on the data on this mock observation. So this is called eROSITA's digital twin. So at any point in the survey, we know what kind of halos we are detecting. We know the input, we know the output, then we can assign a probability of detection based on these simulations. That gives us the selection function, and it looks like this. It's very complicated. This is the probability of detection as a function of count rate for different redshifts, as you can see, and the exposures depending on where you are in the sky. So based on the intrinsic properties of these halos and the exposure time, the place in the sky, right, we actually know what is the detection of probability of these halos. Then we folded into all these work. Took us about 4 years to just basically put that banana onto this plot. Now, you see, this is our money plot, the sigma 8 omega m, right? We can measure sigma 8 with 2% precision. We can measure omega m with 7% precision. This is remarkable for any cluster survey. And here is a comparison. So these contours shows you the previous cluster surveys and their contours. And from our first all-sky survey, we already made a factor of 5 to 9 improvement over these results. So you might be asking, so I promised a lot in comparisons of CMB, right, with CMB. So that's how it looks like. CMB Planck measurements are here, and we are up here. So we see a little bit of higher sigma 8, larger halos forming, but omega m is consistent with CMB. What do we see in S8? So now the colors are switched. eROSITA is in yellow. And you can see also as a blue bar, when you combine with the Planck, eROSITA alone is in this top bar, and Planck is in orange. And you can see we are consistent in S8 completely with Planck. The other experiments, late time probes, are here. We do not see any S8 tension between our data and Planck. But that doesn't mean S8 tension disappeared. There's still a problem here. It did not go away. We just need to understand why there is this S8 tension, but we do not see any tension with CMB. So this means basically we see a very similar number of halos forming when we compare the early on in the universe. So here is the dark energy equation of state. Again, this is pressure divided by density. Because we live in a dark energy dominated universe, we are really sensitive to this parameter, and we can constrain it with 5%. When you compare with the Planck, which is an early universe when dark energy was subdominant, and you can see we are very powerful. And here's a comparison with other probes, like, for example, STS-SPAO measurements are in green, and in brown you see the Pantheon supernova 1A and DES 3.2 correlation function. So we are really sensitive to this parameter. And what is important is that the value, this is W0, non-evolving dark energy equation of state, is consistent with -1 as predicted by Einstein. How about neutrino mass? So It's very interesting. We use the most massive objects in the universe, collapsed object in the universe, and we can determine their total masses. These are the neutrinos that you know, neon, electron, and tau neutrinos, their total mass. How do we do this? So I think this is very interesting. The way this works is that when neutrinos enter, they also form early on in the universe. When they enter, right, in the universe and free streaming, the low density fluctuations don't collapse anymore. Nothing happens to the large density fluctuations. They still form massive halos. So by looking at the relative density of these objects with different redshifts, like structure formation, you can measure the masses of these objects. So when we look at eROSITA data alone, we say that their masses cannot be, total masses cannot be larger than 0.4 eV. And Planck is here. They have much better results than us. And when we combine, we think that they cannot be massive, more massive than 0.1 eV, 0.14 eV more specifically. And here is very interesting because the ground-based experiments give us a lower limit. And we get an upper limit from space. So, and ground-based experiments, upper limits, lower limits are very sensitive to the model that you use. But there is now very little parameter space left for all these experiments to agree. I think we are onto something here. So taking this further, we can now look at the sigma 8 because we see a little bit of tension with Planck in sigma 8. And look at how it evolves, right? So my postdoc looked at this, and this is a redshift mapping of the sigma 8 parameters. In every single data point, there are 1,000 clusters. We now have large statistical samples with eROSITA. In comparison, SPT can go out to higher redshift, but there are only 200 clusters in bin. Important thing is that Planck sits right here in the shaded region, and we are consistent with Planck, or our high redshift clusters are a little higher. We see a little higher number of clusters forming at high redshifts, but we think that that's because of the contamination we have in that bin. The rest are consistent. And you can see the sigma 8 tension basically in this plot, S8 tension in this plot between Planck, us, and the other probes. You can also do some other physics. So you can constrain general relativity, how the gravity works in our universe, by introducing a different parameter which will basically affect the growth of the objects, these objects. If you include this gamma parameter on omega m, basically you give an extra free parameter, and then for the general relativity and the gravity that we understand, this gamma is supposed to be 0.55. But with clusters only, we don't see that. We see much higher. That's very consistent with the previous cluster experiments. When we combine with Planck, we are still higher than what general relativity predicts. What does this mean? This is intriguing. We don't know, but it says basically the gravity is weaker than we expect from general relativity, and there is some suppression of the cluster growth in these mass scales. Clusters may form slower than we expected. Another thing is, this is fresh from the oven. This paper is going to be published submitted next week. You can actually use the structure formation to constrain some of the dark matter models. One of the well-motivated dark matter models is called axion-like particles. So axion-like particles are much lighter than cold dark matter, and when you simulate them with cold dark matter, the universe looks very clumpy. So you see massive halos, but a lot of smaller halos. When you simulate the universe with ultralight, with axion-like particles, you don't see that kind of clumping in the universe. In fact, they can explain some of the long-standing cosmological questions like core cause problems in galaxies or missing satellites in galaxies. So we tested these models. How do we do this? They look like, they basically behave like neutrinos. They are very light and fast. And when they, if they are present in the universe, like if your dark matter abundance is made up of ultralight axions, they smooth out the density field and you form less low mass halos. So cold dark matter halo mass function would look like this. If you had axions, or what is called fuzzy dark matter sometimes, the halo mass function would be suppressed in low scales. So that by looking at how many low mass halos we observe and compare with the high mass objects that we see in eROSITA, we can constrain these objects. And as a matter of fact, they are very interesting. Their mass ranges, mass range about 10 to the minus 25 to 10 to the minus 35 EV. So at 10 to the minus 25, they behave like cold dark matter in the halo mass function. Above 10 to 30, below 10 to the minus 35, they behave like dark energy. So we can't constrain the both end, but we can constrain the in between, because basically their de Broglie wavelength is at cosmological scales, at the cluster scale. So when you look at halo mass function, cold dark matter gives you this white plot, white curve. And then if you have 100% ultralight axions, then you don't form low mass halos as much, and you get this purple line. So when we look at the eROSITA data, in the ranges that we are sensitive to, this is where actually clusters, cluster size, 1 megaparsec, is comparable to the de Broglie wavelength of these particles, we get the tightest upper limits. And in comparison, Planck 2018 measurements are shown in red, and you can see we are very complementary. But what do we do? What do we say? What do we see in this plot? This colorful region is forbidden. We are looking at the axion density here and the mass that I was talking to you. Here is the dark energy era. This is it behaves like cold dark matter here. And all this area is allowed by our constraints. But look at the abundances. They are extremely small, right? And actually, what we say, the axion abundance cannot be larger than 3% of the total matter density of the universe. And in most of the parameter space, actually, it cannot be more than 1% for these masses that we are sensitive to. So we are ruling out these ultralight axions from the structure formation point of view. I promised you to show some of the exciting astrophysics we do with eROSITA. So we're just going to close down the cosmology here. And I think some of you really would enjoy seeing some of the astrophysics here. We talked about these massive objects and how we can constrain cosmology with them. But let's talk about these very interesting galaxy groups, shall we? They look like these beautiful flowers in the sky, by the way. There is a supermassive black hole right sitting in their center. And this supermassive black hole messes up the environment quite a bit. And we are sensitive to this gas. So we can measure its X-ray properties or thermodynamical properties like entropy, temperature, number density, pressure, etc. And we can know what the supermassive black hole does to the environment. And group size halos are sensitive to these gas motions introduced by supermassive black holes because they're low mass halos. Their dark matter halo is much smaller than galaxy clusters. So one of my students has looked at this problem. What he did here is he stacked more than 1,000 galaxy groups in our sample. And he's looking at the entropy as a function of temperature of these galaxy groups. So the galaxy clusters live in this era. We don't show those. They're not too interesting. But we show you the galaxy groups that we can make an impact. And temperature, you can see this as a mass proxy. So the high mass clusters are here. These are all galaxy groups, right? So what he's showing is that the entropy that he measures is consistent with the maximum AGN feedback. And no feedback scenario does not explain what we see in the observations at all. And here he takes a step further and compares with the other simulations, state-of-the-art simulations like Millennium, TNG Magneticum, and OWL simulations. Not a single one can actually explain the data. So the AGN feedback model in the Millennium TNG simulations is it's very mild. And OWL seems to be okay in the low mass halo regimes, but then it does not explain these medium-sized halos. Magneticum, which is calibrated on the X-ray data, does pretty good job in most of the time, but not in the low mass halo. So there's something in between. And, but what we hope that these new observations will now be used in the simulations to calibrate the AGN feedback models, and maybe we can learn more about the physics. Another exciting results came out from my group this year is that we started looking at some other interesting stuff that we can do with the all-sky survey. And when you have an all-sky survey, you can actually go look at anywhere in the sky. So I don't know if you have heard about these objects, but there are new classes of objects have been discovered in the last 2 years, what they're called odd radio circles. They were observed by the new generation radio telescopes, and they didn't know the origin of these objects, and we basically looked at the location of these new discoveries in our sky. Some of them are in the south, like this cloverleaf odd radio circle. And in fact, we looked in our data, even in the deepest data, we saw nothing. So it was really disappointing. But then what we saw in the same location is the clustering of point sources. We detect point sources really easily. There's 1 million of them in the first all-sky survey. And I told my postdoc, I said, this is so suspicious because there's twice as many point sources in this field than anywhere in the sky, right? There must be a halo here. So then we went and convinced the XMM Newton's director to give us some time with XMM Newton, and he was so nice. He gave us 35 kiloseconds. We directed XMM Newton and detected this diffuse gas in the direction of cloverleaf org. So basically pink gives you the radio data, and blue is the X-ray data. And in the middle of it, there is a bright elliptical galaxy, BCG1, another one here. So what we think is happening here is that two galaxy groups merged, and then we saw them after the merged because we see an indication of shocks forming. When we look at their temperature and density, we said, okay, this is definitely below our flux limit. We would not see it, and you can see the masses are pretty low anyway. So what we think, which gave rise to this really powerful radio signal, is that there was a really cosmic electrons in the medium, which was released by this AGN in the medium. And then when the shock happened, these electrons got re-accelerated and gave you this powerful radio boom. But we don't know. This is just one of the explanations, and we asked more time from XMM Newton and got granted. So hopefully we will detect some shocks in the region. Another exciting result is on the large-scale structure. You remember I said these galaxy clusters are not isolated, but they are connected with the large-scale filaments. Now we are detecting this gas in X-rays significantly. So what we did here, we took advantage of the optical surveys, galaxy surveys. They give you the best, actually most complete filament catalogs. We overlaid on our eROSITA sky. You can see this gray region is the Russian hemisphere. So we don't see this area. It's actually larger overlap with SDSS. But we have some data. Removing the eROSITA bubble, we found about 8,000 filaments overlaid on our eROSITA data. And then we looked at the surface brightness from the filament spine in the orthogonal direction. So that's what you see. And then subtracted the background, which are taken from the random fields. We see about 9 sigma detection of the gas in these diffuse filaments. We subtracted everything we detect, but there are still large number of objects which are below our flux limit, we do not detect, right? But they contribute to the overall signal behind these filaments or in the foreground. So we modeled those out. Those are AGNs, X-ray binaries, or halos, CGM. After doing that careful work, we find 5 sigma detection of this gas. I need to make sure I tell you that the temperature of the gas is in the high side, 0.5 keV. That corresponds to 10 to the 6.8 Kelvin. And the overdensity that we estimate is 30 to 100. And as a matter of fact, you can assume, this is very hand-wavy, I know, but you can assume a certain cylindrical geometry. And when you do that, we can count about 20% of the baryons stuck in these filaments. And this plot shows you the illustrious simulations. There's the temperature of the filaments. There's a baryon overdensity in the simulations. Basically, the filaments live in this area in the simulations. But what we see is in the high end. So we are really seeing the tip of the iceberg. And that makes sense because most of this gas, in fact, emits in the ultraviolet regime, but we don't have a telescope to detect. We have an X-ray telescope, which stops at 0.2 keV. So this is the very hot, dense region of the filaments that we see. This was the last result that I wanted to advertise today from my group. We published a large number of papers from eROSITA clusters and cosmology working group. There are multiple institutes in this working group, but I don't have time to go through all these fantastic results. What is really important is that this data now is public, so you can go and play with it. And if you have any questions, we are always happy to help you. We have about 42,000 clusters that we are working with in the deeper survey now. And our redshift range goes out to redshift of 1.7. So now we're going to be opening up to our studies to the higher redshifts. And I really cannot wait to get my hands on the Raman and Euclid data, where we can actually use this data for the weak lensing mass calibration or redshift measurements and push these measurements to the redshift evolution phase. Thank you very much, and I would be happy to take your questions now.